when I have n not equal to 7 or 6, there's nothing to balance this out over here to give me 0, right? So I can see that b sub n is 0 unless n is equal to 6 or 7. When n is equal to 6 or 7, then I need to choose the b sub n so that it cancels these out, which means I need minus 4 cos 6 over sinh and minus cos 7 over sinh 7. So here you go. This is the solution right here. 4 cosine 6x, cosine 6y, cosine 7x, cos 7y minus 4 cosine 6x. You see it. You see it. You can read it. Now, this is an odd problem, I believe. Right? What did I solve here? I solved number 1 from section 10.7. Right? So I get through this 2.5 pages, 3 pages of work, right? I'm like, great. Woohoo, I'm done. You go look in the back of the book. It looks nothing like this, not even close. It looks weird. It looks like this. All right? So how do you get to that? The thing is, you can collect the cosine terms together and rewrite this cos sinh business like so. And then there's an adding angles formula for cos and sinh, which gets you back to this. And if you factor out the 6 and the 7 here, it's even more natural because you get like 6 times y minus 1 and 7 times y minus 1, which allows you to see what's going on with the formulas because y equals 0 and y equals 1 are special as they relate to the initial boundary, the rectangle. So it's the boxed formula is better, all right? Here's the proof that those identities work. All right, so that was a related but different problem than the one we had on the board here. This one actually, number 3 from section 10.7 in Nagel, Saff, and Snyder, I think edition 4, right? Is it 4 or 5? I have 4. 4, right. I think this problem is taken from 4. You can check me on that. But so here I have 0 voltage on the ends. And I've got 0 voltage on the top, right? And I've got a given voltage function on the bottom. So what I'm looking at here is both H and L are both set equal to pi in this problem. My L and my H are both pi. And all right, so I'm going through let's get to the blank template and get on with it, right? Well, see, See, in this calculation, I actually kind of did something different. Instead of finding the blank template, I found out that the nth one has to have this so like I built condition 3 into the blank template in this calculation. That's another way you could go. I mean, some way or another, you have to face all of the data that you're given and craft it into the solution. I've shown you one way. As you can see, what I did here, I went a slightly different path, see, because I built condition 3 into the blank template, it looks like, right? Although, I didn't actually do it. I mean, I have that up there, but I didn't actually put it down here, did I? So this looks just like our blank template. Sin nx cosh, sin nx sinh, just like I have over here, right? But you notice that the pi's be canceling. Like putting both of them pi is very friendly. You know? You should be like, can we please have a rectangle with pi for both coordinates? We prefer that. Maybe I'll make them like square root of 2 and square root of 3. No, that would just be nasty. Punishing me too, you know? Anyway, so u of x0 has to be equal to, it has to be equal to f of x, but f of x, I'm saying, has got coefficient c sub n. So you can see from this that we have to have c sub n equals to a sub n, right? And you can find the Fourier coefficients like that. Now I think, all right, so So that's the best answer I can give in terms of the Fourier coefficients here. I'm not actually given the f of x in this problem, so that's kind of like the best I can do for the answer. Don't worry, this will not happen to you, but, you know, if a class was especially disrespectful to me some semester, they might find this in their project. This is math that you can, I mean, you should be like, we'd like to do that. That's interesting, right? But somehow, in this part of the season of the semester, you guys get weighed down with everything else under the sun. And so I understand. You got widgets to build and reports to write, group meetings to attend. I understand. I have a meeting myself I'm going to tomorrow. We call it a math meeting, but you know, it's probably not about math. Anyway, so to solve the Dirichlet problem, boundary value problem on the disk, it looks like this. Here it's interesting. So like if you're solving the voltage function on a disk, you get a different kind of boundary condition. You get this periodic boundary condition. See, the voltage function in polar coordinates, what should it do? It must match what it started with. Like you go around full circle, it's got to have that 2 pi periodicity, right? So that gives you a different kind of boundary condition. And but I'm also given that at radius 2, it's f of theta, which for some reason is absolute value of theta. I mean, it's given. But it's kind of neat. You go through the separation of variables that we went through, and when you do that, you end up with r squared r prime prime plus r prime over r equals to minus t prime prime over t equals to k. Well, if you look at that, that gives us a Cauchy-Euler problem in the radial function. So, you know, again, this is why we study Cauchy-Euler in here in part, is because it naturally comes up in actual physical, you know, problems that you might run into. And it takes some work, but eventually you can find the solution, and it's that. So that's the voltage function on a disk where the voltage at radius 2 is as given. So you can do these sorts of things. And you could actually, with the math that I've shown you and some time, you could do things like describe waves on a drum and things like that. I've pretty much shown you how to find waves on a string in here. Okay, what's next is this. So we've only dealt with what are called homogeneous boundary conditions, meaning that both of the endpoints are fixed at 0 or both of the derivatives are fixed at 0, right? Past that, you can look at non-homogeneous boundary conditions. Suppose that the voltage is 1 on one side and the voltage is 3 on the other side. What would you do then? That's a non-homogeneous boundary condition. Well, it turns out you can make a substitution that changes it back to homogeneous. Then you solve that problem, and then you morph back. There's this whole world of extra tricks past what we've looked at. I mean, this is just the start. My brother said he was reading a book on PDEs, because Bill just reads. But he was just kind of shocked, because it finally got to like the penultimate algorithm for how to solve PDEs like this, but a little bit more grown up, a little bit more cases to consider. And the algorithm is like literally 15 steps. There's just so many different wrinkles that you have to deal with. And so that's the sort of nuance that we get into if we actually had a PDE course here. I try to show you guys the basics so that you understand the flavor of how it works, and that if you were faced with trying to solve a deeper problem, you'd know where to start, right? And I also like these problems because I think they reinforce what we did earlier, right? But the other deeper thing that we haven't spent a lot of time in here is Green's theorem. Not Green's theorem, but Green's functions. Green's functions, if you can find the Green's function for a differential equation, it's kind of like licensed to solve it. And Green's functions have a very natural and beautiful relation with boundary value problems. But this is a deeper topic. We really don't get into much in here. That book I was showing you, Haberman, we'll get much deeper. Now we started to get into a little bit of that with the transfer equation and the transfer function and so forth, but we don't really go that far into it in here. So anyway, That's it. That's your course. So what do we have left? We must have a day left, right? What do we have? How many days? That's it, yeah, I think. Am I forgetting something? Did I? Let me look up the course schedule here, see where we are. I think we have some classroom interaction still, right? So you guys are supposed to be giving me mission 2 today, right? Yes, there's that. So make sure you give me your homework before you leave. But yeah, so what is it? Next Tuesday it's all up to you guys. You ask me whatever questions you got about test 2. Like I said, test 2 covers material up to 11:30, which is, oh, that's not honest. That's actually I was in a meaner mood when I wrote this. I will actually not test you on PDEs in test 2. I've in the midst of the semester, I've wised up to that. That's not wise. Now, on the final, there might be an elementary PDE question, like boundary value problem, all right? But then the PDE project 2 is due the Tuesday after that, right? And in fact, I don't think we'll even have class that day, right? So you can use class time to finish the PD project this day, all right? Just make sure the PD project finds its way to my mailbox before the end of business Tuesday, okay? See, let's say that this is due at like 5 p.m. Well, 6 p.m. Tuesday, all right? Because my day ends at 6 on Tuesday. Although the math department's a little sketchy at 6, right? You can't always get in, so you might have to track me down. Oh yeah, you can put it under the door of my office. That works. I'm sorry, I forgot. I do have an office. You're right. Thank you. You want an A in this course, right? Maybe. Ah. What's that? What's that?
Is the project individual?
The project is individual, yes. But you are allowed to talk together, work together. But the results and work must be your own, yeah. Now, if you end up needing to do like integral of x squared times the sine of whatever, you may use MATLAB, Mathematica, Wolfram Alpha, whatever. You are free to use technology. But you do need to, express a solution. Like just writing down the answer to the problem isn't going to work for me, but